So in the last couple lectures, we've seen a number of results for maximizing submodular and monotone functions. So we've seen that maximizing a submodular and monotone function subject to a matroid constraint is, first of all, it gives us a class of hard problems. So it's hard in the sense that there exist examples like max K cover where exact solution or even arbitrary approximation, is NP hard. So we saw that. But on the flip side, we also saw that greedy gives a 1 minus 1 over e approximation for maximizing subject to uniform matroid constraint. And we saw that this is best possible. And we also saw that greedy gives a 1/2 approximation for maximizing subject to an arbitrary matroid constraint. So already that's good. But we're interested in possibly other algorithms. So the next sequence of lectures are going to be on continuous extensions. And these are a different approach for maximizing and also minimizing. So continuous extensions, which I'll define on the next slide, map a different, in other words, not the greedy algorithm, approach for maximizing and minimizing. And they basically try to leverage this idea that we have tools for continuous functions that are powerful. So perhaps we can leverage these. So the idea of a continuous extension is the following: if we're given any function that, for the moment, let's set aside submodularity and let's consider any set function. So any function that maps from subsets of our finite ground set E. So in other words, equivalently, I can think about f as being a function from the corners of the unit cube in E dimensions. And since any corner of the unit cube is essentially the indicator function of my subset. So given any such function, it's natural to ask, can I just extend this to be a continuous function on the entire unit cube? So we ask, how can we extend to a function that goes from the entire unit cube to R? Because once we have, so what this means is a function that agrees with our given set function f on the corners of the cube, but gives some interpolation, some continuous. I don't want to use the word interpolation. Gives continuous result for continuous values, varies continuously for everything else in the unit cube. So there are two canonical extensions, one which gives a convex function and one which gives a concave function. And they're canonical in the sense that it's natural to seek such continuous extensions if the name of the game is trying to find algorithms for minimizing and maximizing. So in this sense, they're canonical. So two canonical continuous extensions are defined as follows. One is called the concave closure, and it gives a concave function, as the name suggests. So here's the notation. F plus is the continuous extension that is called the concave closure of our set function f, and it's defined on the entire unit cube, and for any element x of the entire unit cube, the value of this concave closure is defined as a solution to the following maximization problem. So it is the maximization of the sum of alpha s f of s, where s ranges over all subsets of E, and alpha s is essentially a probability distribution over all of these subsets. So what does it mean? What is required to make alpha into a probability distribution? I need to have it sum to 1, and I have to have each of the elements be non-negative. So I need it to sum to 1. Now you'll note that there's no x yet on the right-hand side. So this is the additional property that we need. And I need essentially the expectation of this distribution to give me back x. So in other words, the sum of alpha s times the indicator function of s should be my point x, which is in the unit cube. And we know that this is always feasible because any point in the unit cube can be written as a convex combination of the corners, and that's all this is. So this is saying, look at for any point in the cube, look at all possible ways to write this as a convex combination, to write that point as a convex combination of the corners. And overall, so those are all the feasible alphas in this set. And now it's just saying, now maximize over those alphas, maximize, solve this. This is a linear optimization problem, by the way, right? Because it's f of s is fixed in this case. Find the one that evaluates the maximum of this value. This is called the concave closure. We're not going to discuss any properties of it yet. We're going to show in the next slide that it earns its name and that indeed it is it's concave. And we're also going to define the convex closure, and we're going to similarly show in the next slide that this is convex, and this is defined exactly in a similar way, but replacing the max with the min. So this is defined as now the min over, just writing out exactly the same thing, sum of alpha s f of s, and again subject to exactly the same constraints. Alpha has to be a probability distribution, or if you like, just it has to define a convex combination of the extreme points. And it has to be a convex combination whose expectation gives me back x, or basically a convex combination that gives me a decomposition of x in terms of its extreme points. So again, let me just write out this observation that the coefficients alpha s can be interpreted as a probability distribution over all of these subsets whose expectation is x. Okay, so now let's show that they're true to their name, and in other words, that f plus and f minus are indeed convex and concave, respectively. So let's show this for f plus, and in fact, the result for the convex closure is going to be essentially identical. So the lemma is that f plus is concave. And again, this is really straightforward, but let's just check the details. So let's take x1 and x2, some elements inside this the unit cube. And that means, by definition, that what's f, not f1, what is f plus of x1? Well, I look at all the possible ways to decompose x1 as a convex combination, and I evaluate f on all of those sets. I take the combination of that. So the maximizing convex combination, let me call that, this is beta s times f of s. And I'm going to not write a max here. Let me also make a small notation here, note here that I've written max and min and not sup and inf, but this is straightforward. This is this is because I'm maximizing and minimizing a continuous function over a linear function, in fact, over essentially the simplex, which is a compact set. So we know that the max and the min are attained. So there's no problem for me saying that beta is the values that attain the maximum in the definition of f plus of x1. And similarly, f plus of x2, these define, this is defined by some other values that give the decomposition of x2. And now let's turn to any convex combination. So let's take x to be some convex combination of x1 and x2 and ask, what is f plus of x? Well, f plus of x is yet another convex combination. It's not gamma, it's delta s of f of s. And this delta s of s of f of s maximizes this quantity over everything that gives a convex combination. So in particular, it's greater than or equal to if I replace delta s by anything else that gives that gives a convex combination of a convex decomposition of this x. But because we have the betas that give a convex decomposition of x1 and the gammas for x2, then, and I know that x is equal to lambda x1 plus 1 minus lambda x2, I also know that if I look at the sum of lambda times beta s plus 1 minus lambda gamma s times the indicator function, this is also going to be equal to x, just following through the definitions. And so this, of course, also is non-negative and sums to 1, and so that's a candidate here, but since delta s is the maximizer, I have this inequality, and I can write that this is equal to lambda beta s f of s plus 1 minus lambda gamma s f of s. And of course, this is exactly equal to lambda f plus of x1 plus 1 minus lambda f plus of x2. And we've just proved that f plus is concave, which is what we wanted to show. And I'll leave this as an exercise for you to show that f minus is convex, but you can see from the mechanics of this proof that it's really exactly the same. All right, so this seems like we've made some progress. We've given any function f, we know that we can come up with two continuous extensions, and in particular, we've found a continuous extension so that one of them is convex and one of them is concave. But we're not done yet, because as you can, a moment of reflection reveals that a priori it's not clear that either one of these can be evaluated efficiently, because in order to find them I need to solve this search problem over over exponentially many variables, all of the gamuts. So that's not good. So we needed some additional work, but nevertheless we have made progress. Okay, so now I'm going to talk about a different extension called the Lovas extension, and this even from the get-go we're going to see that this can, for any function, this can be evaluated efficiently. So we're working backwards. Rather than starting with an extension that has desirable properties like convexity or concavity and then asking can we evaluate it, we're going to now give an extension that is clearly easy to evaluate, but its properties are unclear. And to give away the punchline, the final result of this lecture is going to show that in the presence of submodularity, this easy to evaluate extension, the Lovasz extension, coincides with the convex extension. So that is basically a 10-word summary of the next few slides. Okay, so here's the Lovasz extension. So let's make a few observations. So for any x in this cube, now the previous two extensions looked at all possible ways to write it as convex combinations of the extreme points, but we're not going to do that. We're going to write it as a very special convex combination in the following way. So let's reorder the coefficients if necessary, so that they're in increasing order. Or non-decreasing order. So in other words, x1 is greater than some value greater than 0, but it's less than or equal to x2, less than or equal to x3, and so on. And of course, I could have equalities along the way. They could all be equal. There's nothing stopping, nothing disallowing that. And let's let S1 be the indices of the largest, that correspond to the largest value. So certainly S1 is at least the index E, but if I had equality, it could be more. And similarly, let S2 equal S1 and the indices of whatever the next largest value is, and so on. So let me give an example of this just to make things clear, and I think this will immediately show that we can do this in general. So let's take an element x that's in the unit cube, and let's say 6 dimensions. So let's let x be the vector 0, 1/4, 1/4, 1/3, 1/2, 1/2. Okay, so you see that this is six elements. My ground set has 6 elements, and I've reordered the coordinates so that they're in increasing order, and I do have some equalities. So then, according to this rule above, S1 would be 5 and 6, coefficients 5, coordinates 5 and 6. S2 would be coordinates 4, that's the next largest value, is 1/3, and also what I had before, 5 and 6. And S3 is going to be 1, oops, not 1. It will be 2 and 3 are the new ones, and then what I had before, 4, 5, and 6. And S4 will be everything now, 1, 2, 3, 4, 5, and 6. And note that now I can write my vector x as 1/2 minus 1/3 times the indicator function of S4 plus 1/3 minus 1/2 times the indicator function of S3 plus 1, I'm sorry, this should be 1/4 here, plus 1/4 minus the next smallest value, which is 0, times the indicator function of S4, plus the smallest value, which in this case happens to be 0, times the indicator function of S. I'm sorry, I think that hopefully what I've been saying has been clear, but I've been the indices I wrote have been backwards. So x is equal to 1/2 minus 1/3 times the indicator of S1, plus 1/3 minus 1/4 times the indicator of S2, plus 1/4 minus 0 times the indicator of S3, plus 0 times the indicator of S4. And again, this is just 1/2 minus 1/3 times 0, 0, 0, 0, 1, 1, plus, now I'm going to add back that 1/3. 1/3 minus 1/4 to 0, 0, 0, 1, 1, 1. Now I'm going to add back that 1/4 times to 0, 1, 1, 1, 1, 1, plus 0 times the all ones vector. And hopefully it's clear that we can always write this. So you can also see this basically graphically. If I'm plotting here the values of x1, x2, x3, etc., x4, these are increasing. So all we're saying is, we're basically decomposing in this way. Okay, so certainly we can always do this, and I'll just leave as an exercise that we can always write x in this way. So let me explain exactly what that means, what the way is, and this is exactly the definition of the Lovas extension. So basically, the previous claim that I mentioned says the exercise, that's what I mean by the claim, says the following, that given a function from 0, 1 to e, but I'll write 6 to stick with that example, to r, we can now extend to all of 0, 1 to the 6 by applying f linearly to our decomposition. So again, hopefully this is clear that we've again just come up with that this right here is exactly just a convex decomposition, but it's a convex decomposition in terms of this nested family. So there aren't exponentially many elements to this nested family. But this is exactly a convex decomposition. So this decomposition is one that is considered that's in the feasible set of the convex and concave continuous extensions that we gave on the previous slides. And we just apply f linearly to the right-hand side. So in other words, and I'll use superscript L to indicate that this is the Lovas extension, f of x for our example would be 1/2 minus 1/3 times f of s1 plus 1/3 minus 1/4 times f of s2 plus 1/4 minus 0 times f of s3 plus 0 times f of s4. So this is essentially the Lovas extension. So let's write that clearly. So it's the following. So given in general a function, still have not assumed submodularity here, from 0, 1 to r, then fl for any value x, for any x in in the unit cube, FL of x is equal to the sum of lambda I f of si, where all the lambda i's are non-negative. The sum of lambda I equals 1. In other words, this is a convex decomposition. And the sets S are all nested, however many there are. And so again, for us, these are the values lambda 1, lambda 2, lambda 3, and lambda 4 was equal to 0. And the sets we gave on the previous page. So the one thing to note, which again we get from the previous claim, is that FL is now easy to evaluate. What do we need to do? Given x, we need to find this chain and corresponding values lambda I, and that's easy. And then we just need to evaluate n, which is at most cardinality of E, evaluations f of S0, f of S1, etc., f of Sn. Whereas even this, not only just finding alphas in the previous continuous extensions, the convex and concave extensions, even if you're given the alphas, potentially evaluating them might require you to evaluate exponentially many times the value of f on different subsets. But that's not the case here. So as promised, this Lovas extension is easy to evaluate. The question is now, what are its properties, and is it useful for us? So we're going to conclude this lecture by showing that the Lovas extension coincides with the convex extension, f minus, exactly when f is submodular. So in other words, we're going to show that FL of x equals f minus of x if and only if f is submodular, and I'm not assuming monotonicity here. And what is that going to tell us? Well, this immediately will have some implications on an algorithm for minimizing a submodular function. Okay, so let's prove this. So first, let's assume that f is submodular. Let's prove this direction. Suppose f is submodular. We're going to show that that these two extensions coincide. Now, remember that f minus is defined by minimizing the sum of alpha s f of s over all distributions that whose expectation gives us the point x. And there could be more of those. So let's take alpha s to be the distribution that achieves the value f minus of x. So just flipping back to our first slide where we define these, it's whatever is achieves this. But in the event that there are more than one of these, let's also choose the one that that maximizes the sum of alpha s times cardinality of s squared. And this is by now a familiar friend to us. It's a trick that we've seen a number of different occasions. and what it has typically done is it's selected subsets that have no intersection. I'm sorry, that have complete intersection or no intersection. So we saw that we can use this to select a laminar family. In this case, we're going to show that this is going to select a chain. So in particular, in the presence of submodularity, what implicitly we're going to show is that there is an alpha S that maximizes, that achieves f minus of x that is nested. And because in the Lovas extension, it's clear that that nested family is unique, that immediately shows that these actually coincide. So the claim is that this alpha S, this distribution alpha S, is supported on some chain. So let's suppose that it's not true, because indeed, if it's not true, then it means that we have two sets, A and B, that are a subset of E, and alpha puts positive value on each, and without loss of generality, let's assume that. Let's just label A and B so that this is the case. But critically, both alpha A and alpha B are strictly positive. And A and B aren't nested, which means that A is not a subset of B, and B is also not a subset of A. So now let's use submodularity. So by submodularity we know that f of A union B, this is just the definition of submodularity, and f of A intersection B is less than or equal to f of A plus f of B. So now what we're going to do is alpha B is the smaller amount. We're going to take an alpha B amount of A and B, and in a way that does not increase, that doesn't change the value of f minus of x, but is going to change, it's going to change this. So, so we're going to do the following. Well, let's replace alpha B of A and B. In other words, I'm going to essentially find new coefficients and replace the coefficients of alpha A with alpha A minus alpha B and alpha B with 0. By the same amount of alpha union B and A union B and A intersection B. So in other words, what I'm doing is I'm defining a new distribution, gamma S, where gamma S is equal to alpha S, except that gamma B is equal to 0, gamma A is equal to alpha B minus, alpha A minus alpha B. And gamma of A union B is equal to alpha of A union B plus alpha B, and gamma of A intersection B is equal to alpha of A intersection B plus alpha B. So what does this accomplish? You can see that clearly this value stays the same. Alpha S f of S is going to equal the sum of gamma S f of S, but the value of sum of alpha s s squared is going to be strictly less than the value of gamma s s squared. And I'll leave this as an exercise, but it's a simple exercise, and we've seen these kind of things before. So that's a contradiction. This shows, so this contradiction, we're not done yet. This contradiction shows that indeed the support of alpha s is nested. So it gives us some chain. But looking back at the definition of the Lovas extension, there's only one. There's a unique chain that defines. There's a unique chain that defines the Lovas extension and that could give such a decomposition. So the decomposition into a chain is unique, and that's the result that we want, the first part of the result. That means that f minus of x is equal to fl of x. And again, we used submodularity in a critical way. So we used it here because it was this inequality, the submodularity inequality, that allowed us to conclude that we might had to have this. In fact, I could have written less than or equals to by virtue of that. I'm sorry. We're minimizing, right? So this is the. So I could have written this by virtue of the inequality. Right? We took weight from A and B and we put it into the union, the intersection, but by assumption alpha s was already minimizing. So that's why I wrote equality. Okay. Now let's give the remainder, the last direction. So the converse is what we need to prove is the direction that if f is if the Lovas extension is equal to the convex extension, then f has to be submodular. And that's equivalent to showing that if f is not submodular, then fl must be different from f minus. So this direction here, we're going to prove the contrapositive. So suppose f is not submodular. So what does that mean? It means there have to be sets A and B which violate the submodular inequality. And if we think back to our equivalent definitions of submodularity, I'm going to use one of them. So f not submodular means that there exists a set S, and there exist elements I and j that belong to the ground set but aren't in S. But where we have that f of s plus f of s plus I plus j is bigger than f of s plus I plus f of s plus j. This is again just a statement of decreasing marginal values, where we look at a set S and S union J. That's one way to see it, and it's also an expression of the basic submodular inequality. Okay, so now let's take the set X to be in 0, 1 to the E. Let's take X to be defined by this set S and the elements I and J that we've found. So let's let X equal the indicator function of S plus 1/2 times the indicator function of the set I and J. So in other words, X has values 0 outside of coordinates that are in S or IJ. It has values 1 on all elements of S, and it has values 1/2 for I and J. So what is the Lovas extension? The Lovas extension on X, I need to find my nested set, and the values, the nested set is basically given. It's it's S and then S union I and J. So it's just equal to 1/2, or really 1 minus 1/2, 1/2 times f of S plus 1/2 times f on the larger set, S union I and J. But now let's see, is this also minimizing? So can we find a different decomposition of the set? X is going to basically be 1, 1, 1 on all elements of S, 1/2, 1/2, and zeros. This is what X looks like. So how else could I decompose this? Using the fact that I have this strict inequality which violates submodularity. And you can see what I'm going to do. I'm just going to take values. I'm going to take S1 to be the values of where I'm 1 plus 1 of the 1/2s, and S2 to be the values where I'm 1 plus the other value of 1/2. So in other words, S1 is going to be S union I, and S2 is going to be S union J, and alpha S1 is going to be 1/2, and that'll be alpha S2. And then you can easily check in this case that F minus of X, well, this is certainly going to be less than the distribution I found. Possibly there's an even better one. So it's less than 1/2 times F of S plus I plus 1/2 F of S2, which is S plus J. And there, this is now strictly less than FL of X. And that concludes the proof. So now we know something about the convex extension, and we know that if it's submodular, it is easy to evaluate. And this is important because it wasn't at all a priori true that, why should we have that? So in the next lecture, we're going to talk about other continuous extensions. We have not yet talked about the concave extension and whether or not it is possible to evaluate it or approximate it. We're going to pick this up next.